Έλα ξανά. Ανοιχτό. Ένα, δύο. Εγώ ακούμε. Μίλα λίγο πιο δυνατά.
No. Okay. So now you can hear me. No. Okay. Okay. So we will start with a small introduction. Thank you for participating in our project. Today is the Robotics and AI session. Okay. Why?
Δουλεύει πριν.
Okay. Now it works.
Okay.
So BETES project goal was to educate, engage with a variety of target groups such as unemployed individuals, unskilled employees, long-term unemployed individuals, and in general, people that want to reskill in soft and hard skills. Our objective was to research about the current trends of soft and digital skills. And we created a report based on our research, identified 5 topics that were relevant to the educational material, and we promote our boot camps, and now we are doing the educational material and trainings. Who we are ECECT, where our aim is to empower individuals from different backgrounds to enhance their knowledges with cutting-edge technologies. We have Skills Zone from Malta. We're specialized in skills gap analysis, training content. They have 15 experts in different subjects, including digital skills, upskilling, reskilling, and mainly focus they have on women. We have Digital Idea from Larissa, Greece. It's a non-profit scientific association, and their main focus is in new technologies, education, health, culture, environment, and any other human activity. Here are some of our pictures from the project. Our kickoff meeting, the first TPM in Cyprus, and the second one before 1 week in Larissa, Greece. I mentioned those. We did a questionnaire to find the topics that were necessary to our focus group, and we did a report on survey. So we concluded in those 5 topics, the soft skills, data analysis, AR, VR, Internet of Things, and now the session with the robotics and artificial intelligence. The participation is free for everyone. It's hybrid, and certifications can be received upon completion of a quiz. Our presenter for today is Fotini Georgiou. She holds a Bachelor in Electronic and Electronical Engineering, a Master in Robotics. She has experience in computing, programming, 3D design, as well embedded systems, electronics, and robotics. She did research projects related to digital skills and educational robotics. She do also many other things, other participations. She's a volunteer to the Robotics competition, World Robotic Olympiad in Cyprus. She's a member of the Young Professional Committee with the IET, and she is a national coordinator for the European Robotics Week. So at the end, you have to do the questions in order to receive the certificate. And yes, thank you. So Fotini is going to continue with the session with the robotics and artificial intelligence.
Okay. Hello, everyone. My name is Fotini Georgiou. I will be doing the presentation today for robotics and AI. I know that not all of you are experienced in engineering, so I'll try to explain them as well, the concepts of engineering and robotics as well as I can. Here is what we're going to cover today. We have the foundation of robotics and mechatronics, programming and control systems, artificial intelligence and machine learning, and advanced robotics and emerging technologies. So I'm going to start from the history. I think this is very important in order to understand how fast robotics and then technology expands, and how fast things are changing. So the first person to introduce robotics, well, the word robot, was Karel Čapek, a Czech writer. The word means forced labor, which is what essentially robots do. They're doing a labor for us. And the second person that's also an author writer is Isaac Asimov in 1942, which he introduced the 3 laws of robotics. The first law is a robot may not injure a human being or through inaction allow a human being to be come to a harm. The second law is a robot must obey the orders given to it by human beings, except where such orders will conflict with the first law. So they will do whatever we tell them to do unless they will harm a human being. And the third law is a robot must protect its own existence as long as such protection does not conflict with the first or the second law. So it will have a mind of its own, it will protect itself, but again, it will follow the orders and not bring harm to a human. These obviously were laws made by a writer. It doesn't mean that they are actually applied yet to robots. Here we can see the 3 big waves of robotics. From 1940 to 1970, we have the initial development of industrial robots. The second wave, we have advance in computing and sensors. And third wave, we have the introduction of artificial intelligence and advanced sensors and advanced machine learning. So here is a visual representation of the history of robotics. I'm not going to say a lot of things for this, but I already mentioned the 3 laws. Here we have General Motors uses the world's first industrial robot. This is the Unimate, I don't remember the names, but George Devil and Joseph Engelberg, which is actually considered the father of robotics, introduced this robot that was actually used, the first that was used in industrial setting, and he was doing die casting in New Jersey. Then we have drone, the first unmanned drone that was used, well, one of the first that was used during Vietnam War, if I'm not mistaken. Unmanned means without a pilot, so it went by itself. Here we have the first anthropomorphic robot, so it resembles human form. This is called Wabot 1. And it had actually machine and vision. I mean, when it was the first steps of machine vision. Here we have Puma, that was the first programmable universal machine for assembly, and it was used for surgeries and biopsies. 1986, Honda makes this robot, Asimo, that means advanced step in innovative mobility. So they replicated Wabot robot and wanted to make it more advanced. So to be able, this was not as advanced, so it will wobble, it will fall, and they wanted to make something more advanced. Here we have 1997, the first RoboCup. So you can see mobile robots that play football. Another robot is the robot vacuum. It was introduced in 2002. It's one of the most popular robots, the vacuum robots. Here we have, this is Robonauts. if I'm not mistaken, and he was the first to be launched into space. Of course, it was by NASA. It had machine learning, AI. It could levitate to microgravity. In 2012, we have the self-driving car. It passed the driving test in America. And we also have, in 2015, Sophia was introduced, one of the most known robots that resembles human features. And actually, something I found out by doing this presentation is that Sophia has a citizenship in I think it's in Saudi Arabia, 2017. It got its citizenship. So that's just something to think about. Okay, first, before I tell you the term of the robot and what it does and what it includes, I want you to tell me what do you think is a robot and what is not. So if you can scan this QR code and you can answer what you think. It has, you can either scan it or use that code on top. If you need the code, I will say it out loud. Your phone. I'm not going to say that there is no right or wrong answer. There is a wrong answer.
Is there a link somewhere so that we can click the link?
So just go to menti.com and use the code that you see on the screen. You can use your mobile phone as well.
Yeah, I have the Zoom meeting is on the phone and
December
it's
time.
the text is so small that I can't even see it. So menti.com. Okay.
Okay.
So for those that cannot read the code is 19142030.
Thank you, Mr. George.
19142030. Menti.com.
Doesn't know. Okay. So those of you that didn't manage, you can, I have some more questions. You can log in then. So I wasn't expecting, to be honest, to have so many yes answers. No, actually, a robot is not, sorry, a car is not considered to be a robot. First of all, because it needs a driver. But even if we assume that the car is self-driving car, it's still not really considered a robot. And I will tell you why. Because it does not perform a specific task, and it does not have a manipulation, an actuator, or anything that interacts with something. So it's just driving. It's doing only one task. A robot can do multiple tasks. But it does have robotic characteristics because it's programmable, it can be autonomic, and all of that. Okay, so next one. If for those who don't know who this is from a movie, very nice movie. You can check it out later. I will. Okay. Okay, you can answer now. You have him next door? Oh. I'm not gonna spoil the movie for you, but you should watch it. Okay, so it's obvious, I guess, to everyone that it's a robot. Yes, it is a robot that in the movie, it picks up trash and it cleans the earth. So it has a task and it has hands and it's doing it with its hands. So it's a robot. What about a washing machine? I mean, they are smart. for sure. Okay, again, I didn't expect so many yes answers. It is not considered a robot. It has programmability, adaptability. It does spin, so it does have rotation, but it doesn't do many tasks. It has to perform many tasks and be able to adapt in an environment, so it does not do that. Here we have, I think it's very obvious. Mhm. Okay, I'm glad that there's no more yes in this aspect. It is obvious that it's not a robot, it's programmable, but it does not have an actuator, it doesn't move. Again, this is very obvious, I think. If there's a no answer, I will want the person to explain why not. So be careful. I mean, I did spoil it, but it's very, very obvious. Does someone want to explain to me why it is not considered a robot? Probably not. We have this, a drone. I just have a couple more. Okay, again, it seems that there's a misconception of what a robot is. Drone actually is maybe kind of question because it depends on what the drone does and its capabilities, but mostly it has robotic characteristics. I will explain later why. It is a robot, yes. I think I have two more. Yes, this another one. Promise I'm not gonna make you work later. This is AGV or an AMV, which is an automated guided vehicle or automated mobile vehicle. The difference is one has it follows the line and the other one just moves on its own. Yeah, well, I did say that the vacuum is considered a robot, so therefore it is a robot. And the final one. Okay, well, Siri, Alexa, Amazon Echo, and all of these are called virtual assistants, voice-activated virtual assistants, and they are not considered a robot. They do have robotic characteristics, which is the programmability. They have AI, machine learning, and all those advanced programs and algorithms going on in their microprocessors and such, but they don't do a task. I mean, they do tasks, they help you, they talk to you and so on, but they don't perform or manipulate with the environment. So it is not considered a robot. And here is the term. It's an actuated mechanism programmable in 2 or more axes with a degree of autonomy moving within its environment to perform intended tasks. This is from ISO. Actuated is to put in a mechanical motion, and autonomy is to perform the tasks with sensing without human intervention. Therefore, now that this term is here, you can understand that since they do not have a degree of autonomy, they don't move around. Alexa, the laptop, the washing machine, they are not considered robots. They do have characteristics, which is programmable and all that. Here is another few terms from NASA. It's the same things. Robots are machines, they do jobs, and they work by themselves. Okay, so characteristics. What characteristics are obvious? They have a mechanical body. They have sensors, they're intelligent, and it has energy to supply all of those things. What is not obvious is how you use them. Are they semi-autonomous? Are they autonomous? How do they work? How does the actuators move from kinematics, forwards, inverse? We're gonna cover that later. Are they fixed? Are they moving? How do they move? Is there a pre-planned path? Do they move according to what they see, or depends on the robots? And of course, do they have constraints or not? And is it only one? Are there multiple? Are they coordinated? And here is what a robot is. It senses, it thinks, and it acts. How does it sense with input, the sensors? How does it think with the control system and the controllers? It has perception and cognition. Perception is what it sees, and cognition is how it understands what it sees, and how does it do the corresponding decision making. And act is the output, which is usually the actuators. So it will either move or move its wheels, move its arms, depending on what robot it is. Okay, about the applications. As you can see here, the industry is ready for the robots. They have invested a lot of money for industrial robots. And this is the industries that are mostly used in. There are three major categories: industrial and service robots and educational robots. Industrial mostly refers to non-commercial robots, while service robots refer to commercial use. We have domestic, social, delivery, medical, military, search and rescue, space. We're gonna look at all of those examples. Industrial robots are mostly used for these reasons: welding, material handling, and other applications. They increase efficiency, productivity in the manufacturing. Of course, a human cannot do prolonged tasks as the same as a robot can do. And with the same, it doesn't have the same strength, obviously. Here are some examples. This is articulated robots. They are the most complex in the industry. We have the mobile robots, and of course, the combination of those two. We have the service robots here. They're used to help us clean, help us feed the cat, and so on. Of course, they're used to enhance the quality of life. Here we can see the service robots. We have Aibo, Lovot, and Paro. They're mostly used for to enhance again the quality of life, efficiency, and convenience. They're used mostly as companions. They can interact. They understand human emotions and features, so it can react to it as well. They're mostly used for Paro, especially is used for the elderly, for rehabilitation, when they're not allowed to have animals, but animals is very known to help with rehabilitation, stress, and so on. So they use something similar. I actually saw that robot in person. It moves. It's a seal, and it does move, and its eyes rotate and so on. So it does look very realistic in person. Here we have service robots: Cosmo, Savvy One, Pepper, and Omni Robot. Cosmo is a small robot. It can actuate. It goes up and down. Its eyes are closed, and it has It makes it look like it has emotion. It's very good for robot enthusiasts, and you can actually program it. It's not like one thing that it does. That is a butler that actually been used in some hotels. Pepper is also a companion. It can understand, has AI, has all of those features. It's made by, I think, it's made by Aldebaran Robotics, yes. And Omni is a telepresence robot. Of course, it's a service robot because you can have, it's like a fancy Skype or fancy Zoom. You can actually move the robot and interact. So let's say I wasn't here and a robot will do the presentation and then it will come to you and speak to you. It will be the same. It was used a lot during COVID and in universities that had them. And it's becoming very popular now in universities. Other service robots are delivery robots. Sorry. We have some examples here. In other countries, you can see them roaming around. In Cyprus, you cannot. We have medical. Da Vinci is one of the most popular medical robots. It does surgeries. We have CyberKnife, which does full robotic radiotherapy. And the Xenex robot that sprays disinfectant in the rooms. Again, this was going to be very popular during the COVID because the rooms in the hospital were, when it needed to be cleaned, sterilized, all of the rooms and very fast. So this was one way to do it. You have military robots, search and rescue, which all of these have certain mechanical abilities, so they can move around in uneven terrains. And of course, the educational robots that is they're very popular now. It's a new way to learn STEM and explain some technology concepts to students, an easy way to do it. Here in STEM education, that's what they do. Okay, so people think that robots are gonna be a problem, that they're gonna sell their jobs. But as it mentions here, it is a job displacement. It does not take jobs. So a robot will help a human do a work. It won't take its job. Of course, it introduces more jobs as well because you need someone to take after to program the robots. You need someone to a technician to fix it and so on. So it does create more jobs. It has economic growth, of course, for increasing productivity and efficiency faster than one person does, improve quality of life. And most important for me is that it can perform dangerous tasks so that humans don't have to. So let's say if we go for search and rescue or something like that, you have a bomb threat. Is a person gonna go do it, or are you gonna send a robot that you don't care if it doesn't do the job right? So you're gonna send a robot because it's safer to do it. Or if a room is hazardous, I mean, it has chemicals and stuff like that, you're gonna send a robot to do the tasks. If it's not a smart robot, you can teleoperate it if it's difficult to have full autonomy, but it's still a better way to do it than put humans to do it. Again, this is the concerns, the job displacement, privacy. They think that the data are going to be stolen and so on, especially with artificial intelligence. But there are things that's stopping it from happening. Autonomy decision making. Are the robots ethical? It's a question, because I'm going to ask a different question. Are all people ethical? No, but there is something called roboethics. I'm going to show it a bit later that explains that some things must be taken into consideration when building a robot. So it applies ethical consideration. So it will not, as I said before, it will not harm a human. It will not do all of those things. Security, if they're going to be misused, yes, maybe, but again, depending of who programs it and the way they do it, it's not a concern. And social impact, if it's going to have a problem with human relationships, interactions. Some people are afraid of coming into contact with robots, again, because they're scared of it. But I think we're in now an era that is more acceptable than before. So this is an example. These are movies that have robots in them. For those, well, does anyone know what the main concept is for all of those examples? Has anyone watched any of these movies? Yes, I put them in order of my preference as well. So the basic concept of all of those movies is that robots turn against humans. Most times they also have red eyes for some reason. But how can we ensure that's not going to happen? And here is roboethics. As I said, it's taking consideration scientific, cultural, technical tools that they will be embedded in robotics and promote and encourage their development, help preventing the misuse against humankind. And these are some disciplines that will be taken into consideration. As I said, ethics, philosophy, law, sociology, psychology, computer science, all of those things must be taken into consideration to make a perfectly safe, well, almost perfect, safe robot. So it won't turn against us. But there's always the possibility, I guess, for it to happen. And here I'm going to give you two main types of robots. The mobile robots, which is obvious, is the vehicles that move around the environment, and the robot manipulators looks like this. And it's a fixed base joint robots, and they're very popular in the manufacturing industry. Mobile robots, they can be climbing, walking, flying, swimming, driving, and so on. There are some examples here. There we have, is it Spot from Boston Dynamics? Again, we have Asimo. Oh no, that was Robonaut. We have a drone. As I said, drone is considered a robot, therefore it's in the slide. And we also have actually some that act as, they're more advanced, but the last one is showing a robot that moves like a snake. It's pretty advanced. They're very researching it now. And also we have swimming there. And for the wheeled robots, of course, there are the different type of wheels. And for the flying drones, there are different types. So they're fixed wing, they're the multiple wings, and the hybrid. So of course, depending on the application, you will have to choose what is better for you. If it's a high payload, then maybe you will choose the one with more wings, more rotors. And now about the robot manipulator. It has actuators, sensors, and a structural component. The structural component, it has the rigid bodies and the articulations. Rigid bodies are the links, so it's this part here. And the articulations are the joints, which is the part that moves it. I will explain it a bit later. And also it has the end effector, which is the end. So if it's gonna be, it can be a gripper, it can be so many things. It can be actually a paint gun, so it doesn't really, it depends on the application. Here it shows why it's called robotic arm. It's robotic manipulator or robotic arm. It is similar to a human arm. As we have joints, they also have joints, and this is how it looks like. And this is, of course, okay. Show it here. This is the link, and this here is the join. And this part here is the end effector, and this is the base. Okay, so how does it move? It has degrees of freedom. What are degrees of freedom? They are the number of independent variables that define the possible positions or motions. There are two types of degrees of freedom. They're translational and rotational. So it's either moving, rotating, or it's translating. There I have the full degrees of freedom. Actually, I answered the question now, but there you can see forward, backwards, right, left, roll, yaw, and pitch. Roll, yaw, and pitch are also concepts in flying in drones, while left, right, forward, back are for the wheeled robot. So how many degrees of freedom are shown here in the image? How many degrees of freedom in that picture? Yes, there is a wrong answer, which is I don't know, and the right answer, which is 6 degrees of freedom. Because I just actually spoiled the question for you. It's 6 degrees. Not all robots have all 6. As I said, wheeled robots have mostly 2. A drone has 3, and it goes on. Here again, this has showing a 6 degree of freedom robot, that it's not only the arm, but it's also all the human motion. And all corresponds to one thing: the waist, the shoulder, the elbow, the wrist rotating, the wrist bending, and the fingertip. How do they move? As I said, they are rotating and translating. The rotating is the revolute joint, and the prismatic joint is the translation. So it goes forward and backwards. We have other joints. So depending on the application, you have to choose one. The helical has, it's only 1 degree and it's rotating. The cylinder has 2 degrees of freedom. It's rotating and translating, so it goes up. The universal has 2 degrees of rotation, and the spherical 3 degrees of rotation. And also we have different structures. So how do we combine all of those joints? We have anthropomorphic, which is 3 rotational joints, the spherical, 2 rotational, 1 translational. We have SCARA, the selective combined articulated robot for assembly. It has 2 rotational, 1 translational. The cylindrical robot arm, the rotational translational, and Cartesian, which is all translational. This has very high accuracy, and the spherical is very good with heavy loads. And here we can see 6 degrees of freedom. As I said, it's the highest possible. I mean, it's 6 degrees is the maximum that is used now. You could have 7 degrees of freedom, but that will be redundant since 6 revolute joints create the widest range of motion for a robotic arm. But yeah, you can add a 7th and an 8th, but then you will do a more complex system that has no extra value. If you want, we can have a break or we can continue. Can continue a bit more, okay. So as I mentioned before, robot characteristics have sensors for input, control systems for decision-making, and effectors for output. So I'm gonna explain more about the sensors now. Sensors are devices that enable robots to perceive information. Depending on the application, you get different data. So are you having optical sensors? Do you have touch sensors? And they're different types. They're internal, external, passive, and active. I'm not gonna go into much detail for this, but we're gonna see later some examples of sensors, and it will explain which is which. We also have different input. Is it going to be a digital sensor that gives 0 and 1? Is it true or false? Or is it going to be analog sensor that gives a range of values? Here we have some sensors, tactile, motor, and you can see what type they are. EC is the external and PC is the internal, and P is for passive and A is for active. We have switches for the, well, haptic and tactile are pretty much the same thing. Tactile is a part of haptic. Haptic also has kinesthetic, which is a bit different. It's more advanced than touch, but so we also have for speed and identification. So how do we choose which sensors to put in a robot? Okay, it depends on application, but do we want to know the robot's location as well? Or do we want it to just measure, let's say we have an object, is it there, is it not? Do I want to know where is the robotic arm? It will affect the application. So very good sensors for localization are GPS, of course, for outside, laser ranging radar are LiDAR and LiDAR are the most popular in robotics for localization. And I think I have it here, yes. So these robots, the robotic vacuums, as I mentioned, they can perceive the environment, they can see if there are objects and they are avoiding them. So you need, of course, to know where the robot is in this application. And if I go back, here are some more sensors. These are more for environmental applications. So how do they perceive this information? The sensor gets the data, it extracts some features, so it reduces noise, it does some analysis. And if it has a model, it updates that model in order to use it uses dynamic model to predict how it will change. I will explain it a bit later even more. And image processing. Why is it needed? If we're using a camera, image processing is very important. Image processing is a subclass of signal processing, specifically for pictures. It has image compression, image enhancement, and image understanding. I will show you image enhancement. This is an example. The robot might not be able to understand what this picture is showing, but if you reduce the noise, it can tell, well, hopefully it can tell that this is a girl. And here I have another example that is for data extraction. First of all, you may have noticed that these pictures are black and white. Why? Because colors are a very wide range. So we use black, white, and gray to have a smaller scale of colors, and it will be easier to compute. And here we're using edge detection. So it detects a local change in image intensity. So by applying different algorithms, doesn't go from there to there. There's so many steps in between. You use different algorithms. You might enhance this, might change the brightness. You can do whatever. There's so many algorithms that you can use to go from there to there. Again, depending on the application, depending on the image you have to figure out what to do. I'm not gonna go into detail. That's too many algorithms to learn. And here we have another example of how it works. You acquire the image, you process it, and then you compare those data to previous data. And that's where artificial intelligence and machine learning start. Here we have optical flow. This is a great example for moving images, or I will say a video. so you can detect a pattern that is in motion. And in robotics, you can use it to navigate and so on. So this is 3D representation and 2D representation. So you can tell that that robot there is moving because those dots are not as close. You can see the rotation. I will give you an easier example, is this one. So this is the mouse. It has optical flow. Mouse has been in use for how many years, Mr. George? At least 50 years. Yes, for the optical mouse. It has a flow sensor at the bottom, and it recognizes that there is a change in motion, and it actually uses 6,000 samples per second to calculate that. So optical flow is very popular for traffic. They use it to view the cars and if the cars are moving. And especially if you want to know if the robot is drifting or so on, you can use optical. Should I continue to the actuators, or do you want to have a break? No? I will move on, and I will make the break a bit later. Okay, so we talked about the sensors. Now we have to talk about the actuators. What actuators am I going to use? Again, depends on the application. But there are two types, linear and rotary. So it's what I'll explain later. It's rotating or translating. That particular one actually does both. We have different power source. So we have pneumatic that work with air. We have hydraulic that work with water. So the water pressure does the actuation, and or the pneumatic air does the actuation, or the most popular ones are the electromagnetic one that transform electric energy to mechanical. And here are some examples. The DC motors, brushless, stepper motors, servo motors. Again, if you want to have higher torque, or if you are having high payload, you're not going to use servo, you're going to use one of those motors, DC motors. But the servo motors are very popular in robotics. Here you can see how it works. It gets the signal. You have the power supply or the power amplifier if it's needed, the actuator, and it transmits it to mechanical. As we said, there's 3 types of power supplies. And here I'm going to introduce my favorite part about robotics. It's kinematics and dynamics. You want to know how the robot is going to move. It's not just moving forward or side to side. How does it move? This is a whole chapter of science, and a lot of maths go on for this one, and physics. So it's the study of motion of mechanical points, bodies, and systems without consideration of their associated physical properties and the forces acting on them. So in this case, kinematics, you don't care about the forces. What you care is about the movement. Here is a robot arm, and that is a car, because applies to both types of robots. And here is the forward and the inverse. I'm going to get the manipulator example as it's a bit easier. Forward dynamic kinematics, sorry, is when you know the position of the joints, and you want to find out. So you know where this is. You know the angles of this and this, and you want to calculate the angle of this one. And the inverse, the kinematics is you know where the end effector is, and you want to calculate where this is and where this is going to be. this is for a 3-degree might not be that hard, but for 6-degree robot is very hard to calculate. You have matrices and all those maths going on to try and figure them out. And you also have differential and inverse differential kinematics, which you know the joint velocities, and you want to find the velocity of the end effector. And inverse, you know the velocity of the end effector, and you want to find out the velocity of the joints. And here we have dynamics, which is with respect to the forces, torques, and accelerations. How does the robot interact? How does it move? Again, you have forward and inverse dynamics. In the forward dynamics, you know the joint trajectories, velocities, and accelerations, and you're trying to figure out you're trying to figure out the joint trajectories from the torques and the forces. And from the inverse, you know the joint motion, and you're trying to figure out the torque and the force and the actuations. I mean, this is what they look like. Of course, I'm not going to go into detail. All of those are translated into matrices, and you have like 5 pages worth of calculations going on to figure out. This is very useful when you're building a robot. If you wanted to perform if you want the end effector to do a specific tasks, it's not just going to move from one point to another. You have to calculate how it's going to move. So what is the easiest, let's say, the less complex way to go from this point to this point? And have 2 more slides, and we're going to have a break. So those examples, as I showed before, were for wheeled robots or manipulators. Another thing to take into consideration when you're building a robot, I don't know if you're going to build one, but let's say you will. You need, if it's going to be a standing robot, for that example, you need to also take consideration the balance. So you don't want it to fall over. What you want is the center of mass, as you can see there, to be in the support polygon, which is basically the robot's contact points. And of course, it's static balance when it has zero velocity and acceleration. So a robot will, like me, I'm standing right now, have 0 velocity, and my center point, which is here, center of mass, is within, within my 2 legs. So I won't fall over. And we have the dynamic balance, which you're taking consideration that the fact it is walking. So it is a bit more complex. You have to learn about the 0 movement point, which is the sum of the horizontal rotation momentums of the gravitational and dynamic forces is 0. So in order for it to move, that 0 movement point must be again within the support polygon. Okay. So let's say my support polygon is this big. If I do a big step and bend, I will fall. But if I do small steps and I'm still within that polygon, it reduces the risk of me falling over. I could still fall over, but just saying. And the last thing is trajectory and path planning. Path is the order of locus points in the space where a robot will follow, and the trajectory is the path of the path on which timing is important. So I have 3 points. Am I gonna go exactly on those points because it's my path, or will I go in a bit different way just to reduce the time? I think we can take a break now. It's too much information. And I will continue with the control and the programming. in a bit. You can have some food there, some drinks. 10 minutes. It's okay?
Okay, thank you. Thank you. We'll see you in 10 minutes, Bottini.
Okay. Sorry. Hello, everyone. Are we ready to start again, Mary-Rose?
Yes, yes, we are. Thank you.
We are here, yes.
You can stay until the workshop to find out how it works. We can show them what Mr. George is showing everyone, our robots. Let's go. Okay. We have seen what a robot has: an actuator, a sensor, an arm, a leg, a wheel, and so on. But how do we control that? We have a controller, which is the brain of the operation. It's a computing unit that controls the motion of the robot in a programmable manner. And it could be microcontrollers, specialized controllers, or it can be a whole computer. Here we have some methods. It's the main types of control systems used in robotics. We have the open loop control systems and the closed loop control system. This is what an open loop control system looks like. The control system has a lack of feedback. Means that the robot movements are determined solely based by the input commands. So it does not send feedback back to the controller. This is simple, very simple. It gets the signal, it sends out the signal. And these are the advantages. Simple, reduced system complexity, as it does not require the feedback part. And of course, since it's simple, it has lower cost. But the disadvantages is that it cannot compensate for the errors that occur during the operation. So it has reduced accuracy and reduced repeatability. These are used in applications where they need a low precision and the risk of errors are minimal. So they use this for pick and place robots or assembly and stuff like that. And we have control systems, which have feedback mechanism and are more complex algorithms that monitor the movements in real time. So as you can see here, it has the input, the controller, it does control the output, and then it says feedback at the same time. So the feedback and the input work simultaneously and they compare what it does. And here is the advantages. It can compensate for errors, as I said before, and it has high accuracy and repeatability. The disadvantages are that the more complex hardware and software, and therefore it increases the cost. These are used in high precision, accuracy. Sorry, I was wrong. Assembly is uses closed loop inspection, machining. I'm guessing medical robots as well, because they need high accuracy and so many more. We also have different controller types. We have the proportional controllers, the integral, and the derivative controllers. The proportional controllers are proportional to the error. Integral controllers have time, so they correct over time. And the derivative, they detect and resist abrupt changes in the system. They have also combinations, proportional integral, proportional derivative, and the most complex and the most knownly used now is the proportional integral derivative control, PID. That looks a bit like this. So it reads the sensor, it computes the desired actual output by calculating proportionally, integrally, so over time, and derivatives. So it does have the responses, the changes in the system. All those together, of course, it gives more accuracy in the system, the output. Okay, all those need complex maths. As you can see here, there are deviations, complex maths. And complex maths also bring complexity to the system. What we need is something that has less maths. It's more simple. So there's another concept that's called fuzzy logic. Fuzzy means not clear, distinct, or precise. It is blurred. And in the robotics is an approach to variable processing that allows for multiple possible truths, multiple sources of truth values to be processed through the same variable. So I'm going to give an example. Everyone knows Boolean logic, right? Is it hot? Yes or no? It's 0 or 1. But fuzzy logic, it says, is it hot? Very much, 0.19. Fairly so, 0.75. Moderately, somewhat, very little. So this is obviously it's better than Boolean logic that it's only true or false. But it's much simpler than using those complex mathematics that you use in controllers. Another important thing that I didn't mention is how does the robot work? So it needs an energy source. It can use electric batteries, power adapters, solar power, wireless, pneumatic, and hydraulic. I mentioned those. And here are some examples. Electric generator, solar cell, and so on. Now we're going to move to the programming of those controllers and the simulations you can do. So we have the programming languages. The most common are C, C++, Python, Java, Scratch, and MATLAB. Programming environments, Arduino IDE, LabVIEW, RobotDK, ROS are the most popular. So what does our RobotDK do? It's an offline programming and simulation software for industrial robots. You can use it for many applications. They have huge library that has most of industrial robots. Like one of them is KUKA. And it has examples. So it has a pre-program and pre-simulations of robots like this one. I will show you one later as well. And you can, when they have a simulation, they have a program, you do it step by step. It's not like a code. You just press your end effector, you move it to a 1 position, and then you set it as a target. So that's how it works. It doesn't require very difficult programming languages and so on. So everyone can try and use it. And of course, you need to remember all those things we said about kinematics, dynamics, how does it move around, the rotational and the translational, because you might need to rotate and so on. It's very easy. I will show you an example later. We have ROS, the robot operating system. This is very much more complex than RobotDK, because this one you actually program as well. It's not just a simulation. It's an open source meta operating system for robots, and it provides all those services like hardware abstraction, low-level device control, implementation, message passing, etc. So the main thing you have to keep from this is ROS is a platform that supports code to be reusable in robotics and in research and in education. So everyone can share their code. It can be manipulated, it can be reused. It's very, if you have knowledge of robots and programming languages, it is very good and is suggested to be used in robotic versions. Here you can see what it includes: motion planning, computer vision, data logging, machine learning, and all those things. And I will try to explain a bit of the concept that are used in ROS. They are the nodes, the messages, the topics, and the services. The nodes communicate with other nodes, and they perform a computation. They send, sorry, the messages can communicate, nodes can communicate with passing messages, topics can subscribe and publish a topic. Services has to do with the service clients, and master is the provide a name and registration. You can see there that the messages are published and subscribed, and they're sent to different nodes. And here you have our VIS, which is a 3D visualization tool in ROS. So of course you can already tell it's much more complex than Robotics. This has actual depth and image processing. It's not just a robotic arm. It is used in education, but is used in research as well. So we mentioned all of those things. They come together: the sensing, the understanding, the acting, the learning, and the technology. I'm going to give an example of the Atlas robot that has sensors. It has LiDAR sensors, stereo cameras, and it has, for the actuation, it has wrists, hands, hydraulic actuators. It also has protective cage, low-set arms, and has wireless antennas and onboard battery. So you can tell that that robot can jump, but it is very complex, and I will show you why. Because it requires 2 computers in order to work. It has one on board and one on the control station, because it has a very fast and very complex behavior and dynamic. That's why it needs so much computational power. I suggest you check this out. Actually, it's very interesting how it works. And here are the sensors that we mentioned. Artificial intelligence. I'm going to go back to the history again. The first person to introduce artificial intelligence was Alan Turing. He wrote a paper that called Computing Machinery and Intelligence. And what was the test was basically you have a computer and a person that are hidden. And you have a second person, that's the judge, standing outside, doesn't know which is the person and which is the computer. And it gives them a question or a task to do. And when he sees the results, can he tell which is the human or can it not? So if it cannot tell, the Turing test is basically to exhibit if you can determine the difference. What we're trying to do now with artificial intelligence is to try to make it as you know, the hardest to distribute, to understand whether it is a machine or a human. And here we have the father of AI, which was a computer scientist, and he applied this logic of the Turing test and created the first AI program. As it says here, is the science of engineering making intelligent machines, replicating human intelligence, of course, and intelligent computer programs. It's the interdisciplinary field, so it has so many other fields that go on in artificial intelligence. They deal with models and systems, and as I said, human intelligence. Here we can see AI subsets. Artificial intelligence has machine learning and deep learning. Machine learning is when you use statistical methods to improve with experience. So as it's called machine learning, it does learn. So you give him something and they will learn and will adapt accordingly. And you have deep learning, which is even more advanced, and it has multi-layer neural network features. I will give an example in a bit. So here I explain what it does. It identifies patterns, makes predictions, learns and analyze data sets. It has many learning techniques, including linear regression, logistic regression, decision trees, support vector machines, and clustering algorithms. Again, I will show examples in a bit. And there is supervised and unsupervised learning. Here it is. Have supervised, unsupervised, semi-supervised, and reinforcement learning. And this is just the machine learning, not deep learning. And actually, you also have a part of supervised learning is deep learning. You have classification, regression, all of those things. And these are the concepts and these are the type of algorithms that you can use. Here is an example of classification. As you can see, you have this data and you want them to separate. The dots are this thing and the triangle are this thing. So it can represent anything. It can represent a person and an object. And there you have regression, which you have all the data in one place and you're trying to try and, well, classification gives a pass, fail, yes, no, and the regression gives a percentage. So if it's close to the line, then it's more likely to be that thing. So if you're looking for a human, if it's far, far away, then it's unlikely. So it depends on the application. You use different, these are the simplest I could find, but there are very, very much more complex types. And here's another example. What will be the temperature tomorrow? It's a degree, and classification, it will be cold or hot. So if you remember before I mentioned fuzzy logic, it works something like this. And this is how to confuse machine learning. So here we have some puppies and some muffins. If you give this data set to a machine learning, it will learn, it will think that this is the dog. If you teach him that that is the dog, then it will be identified as a dog. It doesn't matter that it's a muffin. That's what you taught them. And the same thing goes with the other puppies that looks like a fried chicken. If it looks like a puppy, it will also look like a fried chicken. So depending on your algorithms and your analysis, data sets and what images you use to train your models is very important in the programming stage. And here we have deep learning that uses complex pattern of data. And actually, I will skip, I will go here. This is a simple neural network that works in machine learning. So you have all of these are identified as, let's say, dogs. So you have all those and it compares and it could tell that's a dog. But if you have different kind of dog, or if you want animals, so you don't only want dogs, so you have dogs, zebras, and also, so you have so many layers and it can come as an output, yes, this is an animal. So obviously, if you don't need to have deep learning, it needs much processing power, you won't use it. You can use just a simple neural network. Here is an example again. All those are people. And you use one layer for face features, one layer for contrast, one layer for face. So depending on what you want to find out. If it's something complex as a human, of course, you will need deep learning for it. So this shows exactly how all of those work together. Again, You have the environment, the data, the feature extraction that we said if it's an image, it has to be enhanced, it has to be analyzed. It goes to the model, it goes to the machine learning, and it does the decision making. All those work together. And here is my favorite part again. It's advanced robotics. This slide is wrong, but I'm gonna skip it. We have collaborative robots. A collaborative robot is usually a robot arm. And of course it says collaborative robot, it's a cobot. As I said before, we don't look to replace humans. We aim to work with humans to make the job easier. In that particular example, the girl is moving the arm without having to touch it, right? Let's say she wants to pick up something very heavy, she cannot. But it can show the robot the movement that it needs to do, and the robot will pick the object up and she won't do it. Here I have another example. This robot helps this man here. Let me try to, I guess I cannot skip. I cannot skip, so you have to see it. So this robot helps this man in some sort of assembly. You don't need to have robots do everything. There are some things that are just too complex now to, I mean, you can, with the technology that exists, you can do it, but it's too complex, too expensive. So you can still have a human do the dexterous work, the hard work, and you can just have the robot assist. Doesn't have to pick heavy loads, it can just help. And here is another example with KUKA medical robotics team. So I showed you before that there are already Da Vinci and all those robots that work in medicine. Some of them, the doctors don't even do anything, but they are there to assist in case anything happens. The robots are not ready to take this kind of responsibility. And if some of you may have seen that viral video that a robot did the first surgery on a grape, that was also a very huge step in medicine because it requires very high precision. So you can see that they still work with humans. Something that actually needs to be taken into consideration in collaborative robotics is human safety, of course. So there's not every robot can be a cobot because it needs to have high level, high accuracy sensors that can sense the human that's next to them. I read so many papers on that. They need so many things that they need to take into considerations, and they have robots that when they sense a person, they will just stop. They shut down. Of course, you don't want this kind of heavy robot to hit a person in the face. So not every robot is a cobot. That's not a cobot. I mean, I can work with it. It's very small, but it doesn't have the intelligence to understand when my hand is near, so I could get hurt. So you also need human intelligence to step away from a robot as well. Here we have soft robotics. It's a subfield of robotics that has the fabrication of robots composed of compliant materials instead of rigid links. So all I showed before was wheels and rigid links. But soft robotics introduces the concept of a soft robot. Here you can see many different kinds of robots that use silicon or something like silicon, not great with material science, but it does go, you do need a lot of material science to go into this. And as you can see, before we imitated cars and humans, and now we can actually imitate animals. So a snake, spider, even a fish it has a lot of science behind it, because you have to carefully examine how all of these animals move and to try to replicate that, because what we've done up to now was just the arm and the wheels, which is relatively easy. And these usually work with pneumatic or hydraulic. Actually, it doesn't, because it needs air to move or water, depending on the application. Of course, a soft gripper, which is very known. I actually have it. Do we have soft gripper? You can find. So of course it can be both. Can be a robotic arm and a gripper, which is basically a soft robot. But of course this is not complex. It just opens and closes. Does not move around. Here we have Sophia robot, which is a soft pneumatic helically interlayer actuator. This is actually a robot I worked on when I was doing my master's in robotics, and I did some simulations on how big and small these layers of these strands can be, in order, because if you're going to medicine, you need to be very specific. You need to be have a high accuracy. You have to have safety. That's why you use soft robotics. You can't put a rigid thing in a person. I mean, you can, but it's painful. So you're trying to minimize that. And we did a research on how small that can be, because this is specifically for long gap esophageal atresia, which is basically when kids' esophagus stops there and there's a gap. There is a surgery, of course, to fix this. They use it to, it moves. So you move like some rigid parts and it generates the esophagus. Or you can either put, how do you call it, implant from another person, or from, obviously that's a very hard and invasive surgery to do, because they actually put it on the back of the babies and they move all those strings. So if you want to do something minimal, this is a solution. And again, this was using pneumatic supply. And all those black things you see is the constraints. So the robot will go up and on the side. And here we have micro and nano robots. So of course, we have all of these robots. We want smaller ones, especially in medicine, again, biomedical field. They already have some ingestible robots that you can use in order to track something like, is the intestine clogged? They will put something in, you will eat it. If it stays there, it means it's clogged. They can tell by the GPS or other sensors that are on it that is not moving properly. But I would like to introduce these robots. Well, just don't want it to be too loud, but. So as you can see, these robots are even more advanced.
robot forms itself on the spot and accomplishes tasks, and then it disappears by degradation. The robot self-assembles using a folding process that is triggered by heating. After this, the robot can run along designated trajectories, it can carry objects, it can clear obstacles, it can swim, it can execute a variety of tasks. And when these tasks are done, the robot can recycle itself by dissolving its body into a liquid.
This is the first robotic device that completes a full life cycle from its birth to its death. Typical robots consist of electronic devices. Our robot is made based on controllable materials. This is the biggest difference.
The robot's body has embedded in it a small magnet, and this allows us to control the robot by programming a magnetic field. In other words, the robot has external programmable actuation.
Currently, the robot is controlled remotely by a person. We'd like to advance this robot and make it more intelligent such that it can make decisions by itself.
Origami-inspired robot designs have the potential to be faster, cheaper, and easier to fabricate than robots created using traditional manufacturing processes.
It is easier for such a system to be used closer to humans, such as in the human body. For example, you could regard this robot as a controllable drug capsule or a surgical tool, which can be removed after its use in the body.
Can imagine ingesting these robots and then controlling where they travel in the body. And once they arrive at the correct location, they could form themselves into active instruments that can actually manipulate and help through the healing processes. For the short term, we see these robots as potentially extremely useful in inspection tasks because they are small and they can travel through very intricate, small, narrow pipelines that are difficult to inspect with today's technology.
So of course, anything that has to do with medicine is still in testing stages because there's so many things to take into consideration in medicine. They actually, for the soft robot that I showed you before, they did some testing, but in pigs in testing, not human. So it still has a long way to go. Another advanced robotics is swarm robotics, which you have to coordinate all those robots to work together, avoid each other, and perform a certain task. It can be their walking, driving, flying, and the last picture shows that they actually combine each other and create another robot. I'm not sure if that actually exists or if it's just the potentials, but still very fascinating. We have here an example of robots that can write their own code. Okay. So I mentioned all those algorithms and all those machine learning. So these robots can write their own code by using pathways language model. So it perceives the data and then it corresponds to it. And I think this is very recent research. Mm-hmm.
So instead of programming the robots using traditional programming languages, you just tell the robot, arrange the block as we see here, on the top right, arrange the block in a square around the middle, make the square bigger, so forth and so forth. What we see here is that using LLM, long language models like ChatGPT, that instruction array, the blocks in a square around in the middle, that translates to an instruction to ChatGPT, let's say dedicated ChatGPT, and that ChatGPT creates a code, and that code is sent to the robot. So using natural language these days, to use natural language and make programming of the robots more accessible using artificial intelligence.
And here we have
The Ocado Smart Platform, or OSP, is a configurable end-to-end commerce, fulfillment, and logistics platform built to meet the unique demands of online grocery.
OSP enables a winning proposition for customers while delivering the best economics for retailers. A highly personalized online journey delights customers with intelligent features that inspire new choices, help them to find their favorites, and anticipate when they're running low. For retailers, this means improved customer acquisition and retention and greater share of wallet. This enables powerful retail in every level. Benefits.
Before I go into this, and if you have any questions, you can ask me. The last robot showed a combination of what I mentioned before, cobots, because they did work with humans, and it did show swarm robotics, so they all work together as a whole, and they use AI and all those tools to understand the objects that they carry and so on.
Or just to note that online participants can also ask questions, and all answers will be available for all users at the online platform as well.
Does anyone have any questions? I'm going to take that I explained it very, very well. That's why you don't have any questions. Here you can visit our online classroom. We have the quiz that you can do in order to get your certificate. I tried to make it as easy as possible. So to be fair, you could have done it before you came here. And it also has the workshop PDF, and I will actually upload tomorrow all of these presentations, and I will actually add additional material, and the recorded session, because we did record this, will be uploaded there as well. The only thing is just you have to register first, but they're all there, all free. And you can also find our previous topics we did, Internet of Things and soft skills. all of the presentations in there, and they also have the link to the recording as well, which we have a YouTube channel for this classroom as well. Yes, and we're also doing data analytics and AR, VR in upcoming trainings. We already shared the 2 dates. Mr. George, are we doing it the same date as planned? Yes, we're doing it on the 16th of February. We're doing data analytics, and 1st of March, we're doing AR and VR. Not sure if we're still doing it at this location. We will update you with that information. And here, if you please can fill this form and let us know if you like the presentation, if you would like to have more interactivity and so on. Of course, for us that are physically, we will have a workshop later. For those that you're online, we will eventually come to you and do a workshop. Set that.
Well done, Potin. It was very, very interesting.
It was beginner to intermediate. It wasn't advanced because I knew that there would be people that are not don't have knowledge, so I tried. Thank you as well. We're gonna do a workshop now for the online participants. That was it. I hope you enjoyed the presentation. I hope you review the material that we have online. And of course, if you have any questions, feel free to send an email or send a comment on the platform. Thank you again. I'm looking forward to seeing you in Malta and having the workshop with you.
Thank you. Thank you. Bye-bye. Bye.
Bye. Listen to Zoom.